welcome to the first of several tutorials on chains. Chains are one of the most powerful methods we have to solve Sudoku puzzles. It has been said that any puzzle, regardless of difficulty level, can be solved by using only chains and singles. That's quite a statement. If nothing else, it means that a thorough knowledge and understanding of chains of all kinds is absolutely crucial to your becoming a Sudoku master. So let's go over to the puzzle board and get started. Before we talk specifically about X chains today, I want to talk about the logic of chains in general for a moment because they play such an important role in so many of the known solving techniques. And then at the end of this video, I will be adding a bonus section that will serve as a brief introduction to continuous loops using X chains as the model. So I hope you stick around for that. My formal tutorials on both continuous and discontinuous loops will come later on in the course in videos number 38 through number 44. Chains can be made up of single candidates or of bi-value cells or of what are called group nodes and almost locked sets, etc. There are all kinds of ways to construct chains and all kinds of intentions and purposes for them. A chain is simply a series or stream of inferences based on a starting premise. Sometimes a single chain will prove nothing, but will require one or more additional chains analyzed together in order to lead you to a valid conclusion. For instance, if two chains starting with opposite premises, like first assuming something is true and then assuming it is false, lead to the same conclusion, then we know that conclusion must be true. And as we know, this is called a verity. On the other hand, if a single chain leads to a contradiction, then the premise must be false. And likewise, if several chains starting with the same premise lead to all candidates being eliminated from a single cell, or lead to all instances of a particular candidate being eliminated from a house, then again, we will know that that premise must be false, as this result would be an impossibility. And lastly, when we have an open-ended AIC that starts and ends with a strong link and is reversible, i.e. it will make sense by starting on either end, then we will know with absolute certainty that at least one of the endpoint candidates must be true. And if those endpoints are the same digit, then we can eliminate all other instances of that same digit candidate that can see both ends of the chain. This is the case for an AIC Type I. Today we will be talking about X chains. An X chain is simply an AIC Type I that uses the same digit candidate throughout. It is a single digit pattern. All nodes of an X chain will be the same digit, just like we saw with turbofish, two-string kites, and skyscrapers. These are all single digit patterns and they are all X chains. So an X chain is exactly like a turbofish, except that it has more than just 3 links. It's as simple as that. I assume you are all familiar with strong and weak inferences by now. If not, please go back and watch videos number 3 and number 4. All chains alternate inferences between strong and weak. An X chain always starts and ends with a strong link or a strong inference. A strong inference begins with the premise of something being false, leading to something else being true. Then, continuing on from there, we must use a weak inference with the premise of that second something being true, leading to something else being false. Then, continuing on from there, we use a strong inference with the premise of that third something being false, leading to the next thing being true, and so on and so forth. So the nodes will alternate being false and true, or off and on, or however you want to think of it. This is the only way we can make sense out of a chain. But the most important thing to remember is that this does not mean that all those things are absolutely false and true. We are starting with a premise, folks, a supposition, not a fact, okay? We are saying that if something is false, then the next thing would be true. If and would be are the key words. I get so many letters asking me about this. Many people mistakenly think that we are saying that A is false instead of supposing that A is false or asking, what if A is false? There is an enormous difference. We don't know if A is true or false. We are simply trying to analyze the situation by asking logical questions and making conditional statements. If A is false, then B is true is a conditional statement. We are asking or supposing if A is false, then what would be the consequences of that? We are just building a chain of inferences starting with a premise or a supposition to see where it might lead. Then we look to see what conclusions can be drawn, if any. And you must fully grasp and comprehend this concept in order to understand loops and other types of chains that we will cover later on in the course. As I said, when we use the term X chain, we are implying that the chain is longer than just 3 links, because we have special names for 3-link X chains, which are turbofish, 2-string kites, and skyscrapers. And of course, because we are alternating the links, and because the X chain must begin and end with a strong link, there will always be an odd number of links, like 5, 7, or 9, and so on. But please know that because an X chain is a single-digit pattern, it is probably not going to be much longer than 9 or 11 links. It will be a rare occurrence when you can link more than 12 instances of the same digit together. And don't forget, if an open-ended chain has 5 links, then there will be 6 nodes or candidates involved. Some people might say a chain like that is of length 6. But I always refer to a chain by the number of links rather than by the number of nodes. So an open-ended 11-link chain will have 12 nodes. The number of nodes will always be equal to the number of links plus 1. Got it? All right, let's go through a couple of hand-drawn diagrams before we get to the real puzzle examples. If there are only 2 instances of our X digit in any given house, then there will be a strong link between them. That would be a conjugate pair. The strong links in an X chain are always going to be conjugate pairs. When you turn on the filter for a particular candidate and see a lot of conjugate pairs all over the place, this is the tip-off for you, or the signal, that there is very likely an X chain waiting there for you to find and put together. Conjugate pairs are the key. Without them, there is no X chain. And if there are 3 or more instances of the X digit in a house, then there can only be a weak link between any 2 of them. And don't forget, a strong link can always be used in the role of a weak link because it has the properties of both, but not the other way around. A weak link cannot be used as a strong link. And when we use a strong link as a weak link, I like to call it a surrogate weak link to differentiate it from a conventional weak link. So really, the X chain could be made up entirely of strong links as long as there was an odd number of links. Don't forget that. The X chain must have and can only have an odd number of links, like 5, 7, 9, or 11 links. So the result of an X chain is that at least one of the endpoint candidates must be true because there is an effective strong link between them by virtue of the chain of inferences, even though they do not see each other. If either one of them is false, then the other one must be true. If A is false, then B is true. This, of course, means that any other same-digit candidate that can see both ends of the chain must be false. If you have watched all my previous tutorials, you should be very familiar with this concept by now and should have no doubt about the truth or validity of it. When the 2 endpoints of an X chain lie in 2 different chutes, there can be a maximum of 2 possible eliminations, but generally there will be only 1, if any. And when the 2 endpoints lie in the same chute but not in the same house, there can be up to 4 possible eliminations, but generally there will be either 1, 2, or 3, if any. The reason for this is that the presence of other instances of our X-digit candidate in some of the cells that can see both endpoints might possibly negate one of the strong links and would therefore negate the whole X chain. Let me show you what I mean. All right, here we have an X chain of 5 links. Let's start up in row 1. There are only 2 candidate 3s in row 1, so there's a strong link between them. They are a conjugate pair. So if this blue 3 is false, the yellow 3 must be true. And if the yellow 3 is true, then that negates all the other 3s in column 1, including this one, so this blue 3 must be false. That's a weak link. Now there are only 2 3s in block 4, so that's a strong link. If this one is false, that one must be true. And if this yellow 3 is true, this is a weak link over to this 3, so this blue 3 must be false. And if that blue 3 is false, then this yellow 3 down here must be true, and that's the other endpoint of our chain. So either the blue 3 in row 1, column 4 is true, or the yellow 3 in row 7, column 9 is true. All right, so now I'm going to have to remove these arrows to make this next point. So the 2 colored cells are the endpoints of our chain, and there are 2 cells that can see both of those endpoints, and they are here and here, okay? But there cannot be a 3 in this cell because that would negate the strong link in row 1 and it would negate the strong link in column 9, so there would be no X chain. So that can't be there. But there can be one here, and in this case, this 3 in row 7, column 4 can be eliminated as false because it can see both endpoints of the chain. And don't forget, you can run this chain backwards. You can start on either end like this. Strong, weak, strong, weak, and strong. So that means if this yellow 3 in row 7, column 9 is false, then the blue 3 in row 1, column 4 is true. Or the yellow 3 could be true all by itself. This ensures that one of those endpoints must be true. The only way you can have 2 possible eliminations when the endpoints lie in different chutes is if the first link and the last link are on diagonals within a block, like this. Strong, weak, strong, weak, strong. Okay? So the 2 cells that can see both of those endpoints are here, and they can both contain a 1 because they will not spoil either one of those strong links because they're on a diagonal. Here, let me draw it again. As you can see, the 2 strong links at the beginning and the end of our chain are unspoiled by the presence of those 2 red-colored ones, so they can both be eliminated as false. And when the 2 endpoints lie in the same chute, like you see here, there are 6 cells that can see both endpoints. But let's take a look at what's going on here. Those 6 cells are here, here, and here, 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 and here. They can see the 2 endpoints. But there cannot be a 3 in either one of these cells because that would negate our first strong link. This strong link is within a block, so there can't be any other 3s in that block, otherwise it would negate that strong link, okay? And then up here, there can't be a 3 in this cell because that would negate our strong link in column 5. So in this configuration, you could eliminate a candidate 3 if it was here or here, but nowhere else. So because of the shape of this X chain, there can only be 2 possible eliminations, those 2 red 3s up in row 1. All right, here again, our 2 endpoints lie in the same chute, and so there are 6 cells that can see both of them. And they are here, 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 and here. Those 6 cells can see both endpoints of the chain. But there cannot be a candidate 5 in any one of these cells because it would spoil the strong link that's in column 9. But here, there can be a 5 in every one of these cells because that doesn't interfere with any of the strong links. So in this case, you can have 3 possible eliminations, those 3 red-colored 5s. And lastly, here is an X chain of 7 links where the endpoints lie in the same horizontal chute. And again, there are 6 cells that can see both of those endpoints. And they are here, 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 and here. But there cannot be a 9 here because that would negate the strong link in column 2. And there can't be a 9 here because that would negate the strong link in column 5. you could eliminate 9s in these 4 cells. Okay? So in this case, you would have 4 possible eliminations. And as we will see later on in this video, when the 2 endpoints of an X chain lie in the same house, this will constitute what is called a continuous loop, in which there can be many more possible candidate eliminations. Obviously, because we are using the same candidate throughout, all the links will be between cells. With an X chain, there will never be any links within a cell. That would be impossible. There cannot be 2 instances of the same digit within a single cell, like there cannot be 2 7s or 2 8s in one cell. And don't forget, an X chain is reversible. This means you can start on either end and it will lead you to the exact same conclusion that at least one of those endpoints must be true. Got it? All right, let's take a look at some real examples in some real puzzles. All right, here in this puzzle, let's turn on the filter for candidate 2. Now, whenever you turn on the filter for a particular candidate and see that you have 3 or 4 conjugate pairs, there's a good chance that you can build an X chain or at least do something with them. And when you have 5 or 6 or more, you can be 99% sure there is some kind of solving technique available. You should watch for conjugate pairs all the time because they play an enormous role in so many of the solving techniques. They are a central part of X-wings, swordfish, turbofish, skyscrapers, 2-string kites, empty rectangles, W-wings, AICs Type I and Type II, and continuous and discontinuous loops. Conjugate pairs and bi-value cells are probably the 2 most useful and important things there are to help you solve any puzzle and to find all the different patterns related to all the solving techniques. So you should watch out for them at all times and always be aware of their presence. All right, we've got an X chain here, and first I'm going to mark the endpoints. These are the 2 endpoints. So we can start on either end of the chain, but let's start right here. And we're going to use blue to yellow is going to be a strong link. So there's a conjugate pair, there's a strong link, and then there's a weak link over to this 2, but that's really a strong link, but we can use it as a weak link. That's a surrogate weak link, all right? Then this is a strong link, that's a weak link, a strong link, a weak link, and then finally a strong link. And so there are the 2 endpoints, and that means this 2 and this 2 are false because they can see both ends of the chain. Now I'm going to draw the chain this time, but I'm not going to do it on every puzzle because it would take too long. But let's do it here. We've got strong, weak, a surrogate weak, strong, weak, strong, weak, and finally a strong link down to this 2. So one of those 2 endpoint candidate 2s must be true, and so we can eliminate both of those red colored 2s. All right, let's go to the next one. All right, here in this puzzle, let's take a look at candidate 7. We'll turn on the filter. There are all the 7s, and we've got a few conjugate pairs. We've got an X chain with the endpoints here and here. So let's start on this one up here in block 3, and we've got a strong link, and then a weak link, and then a strong link, and a weak link, and finally a strong link. So that's just 5 links. 1, 2, 3, 4, 5. And so that gives us 2 candidate eliminations on these 2 7s. Now notice that these 3 cells can see both ends of the chain, but there cannot be a candidate 7 in there because that would negate the conjugate pair that's in block 3, and it would also negate the conjugate pair in row 3. So there can't be any 7s there. The only 2 that we can eliminate are here and here. All right, let's go to the next one. Okay, here let's turn on the filter for candidate 9, and there are all the 9s, and we've got a bunch of conjugate pairs here, and we have an X chain, I think, of 7 links. It starts here and ends here. Okay, so let's start up here in block 1, and we've got a strong link down to this 9, and then we've got a weak link over to this 9, a strong link up to that 9, a weak link to this 9, and a strong link to that 9 on the diagonal, a weak link up to this 9, and finally a strong link over to that 9, and there are the 2 endpoints. So any candidate 9 that can see both of those endpoint 9s will be false, and this is a very interesting one because we have a cannibalistic elimination. This 9 right here is part of our chain, but it sees both of those endpoints, so it is false. Now this is legal. Even though it's part of the chain, it is false, and you can eliminate it, and this is called a cannibalistic elimination. And the other two 9s that can see both of the endpoints are here and here. So there are 3 eliminations on this one. But don't forget, if a candidate is part of the chain, but if it sees both endpoints, it is false, and you can eliminate it. Okay, let's go to the next one. Okay, let's take a look at candidate 3. And there are 9 conjugate pairs in this puzzle, so we know we're going to find something. And as it turns out, there's an X chain that begins here and ends here. So we're going to start on this conjugate pair in row 4, and we've got a strong link there, and then a weak link here, and then a strong link here, and then a weak link up to this 3, a strong link to that diagonal, and then a weak link over to this 3, and finally a strong link to that 3. So those blue colored cells are the endpoints of our chain, and any candidate 3 that can see both of those is going to be false. And once again, we've got a cannibalistic elimination. This 3 right here can see both ends of the chain, and it is part of the chain. So that is false, and the other candidate 3 is this one. That is also false. And you can eliminate both of them. Now, normally, it would not be possible for an elimination to occur in row 4 because we had a strong link in that row, but because it's a cannibalistic elimination, you can eliminate that candidate 3. All right, next one. Okay, let's take a look at candidate 8, and we have an X chain here of 9 links, and it begins here and ends here. So we've got strong up to that 8, weak, strong down to that, weak over there, strong. Then this is a surrogate weak link. We're going to use that as a weak link, and then finally strong to this 8 in row 9. Now, even though this chain was 9 links long, there is only one elimination to be made, and that's this 8 right there. That's the only 8 that can see both of those endpoints. So that was a lot of work for just one elimination, but that's life, and sometimes that happens. All right, let's go to the next one. All right, here on candidate 1, we have an X chain of 7 links that begins here and ends here. We have strong, weak, strong, weak, strong, weak, and finally strong. So those are your 2 endpoints in those blue cells, and there are 2 candidate 1s that can see both of those endpoints, so you can eliminate both of those candidate 1s. All right, next one. All right, here on candidate 2, we've got a short one of 5 links, and it starts here and ends here. So we've got strong, weak, and strong. So those are the endpoints in those light blue cells, and there are 2 candidate 2s that can see both of them, and you can eliminate both of those candidate 2s. All right, next one. All right, let's turn on the filter for candidate 1, and we have a 7-link X chain that starts here and ends here. So we've got strong, weak, strong, strong. So those are your 2 endpoints in the light blue cells, and once again we have a cannibalistic elimination on that one, and then 2 regular eliminations on those 2 1s. So this one here in row 4, column 4 is false because it can see both endpoints of the chain even though it is part of the chain. So you can eliminate that and these other 2 1s. All right, let's go to the next one. You know, a lot of people ask me how to go about constructing these chains, like where do you start, for instance. Well, my best answer for this is to first mark all the conjugate pairs and then try to connect them with weak links. Remember that any valid link can be interpreted as and used as a weak link. So weak links and surrogate weak links are always plentiful. Another trick is to pick 2 endpoints that you can see will produce some candidate eliminations if you can connect them, and then work backwards from each one and try to connect them so that they meet somewhere in the middle. Okay, here on candidate 1, we have a 5-link X chain that begins here and ends here, and there are actually 2 ways to construct this chain. So let's start up here on this one, and this is a strong link, a weak link, a strong link, a weak link, and a strong link. But we could have gone over to this one and then over to this yellow one in row 7, column 2, but we don't need to do that. Here's our chain, and those are your 2 endpoints in the blue cells. So there are 3 candidate 1s that can see both of those endpoints, and they are up here right next to each other. You can eliminate all 3 of those 1s. Okay, that's going to do it for these X-chain examples, so I hope you all have a clear understanding of how they work now. But before we wrap up today, I want to touch on continuous loops for a moment. Okay, as promised, here is a little bonus section. If after a couple of minutes you feel that this is a little too advanced for you, you can skip this section today and wait for the full tutorials on loops coming up later on in the course. As I mentioned earlier, there are many different kinds of chains. For instance, a chain does not always have to start with a strong link, but an open-ended chain that starts with a weak link will not tell you anything all by itself. You will need other information to use in conjunction with that type of chain to draw any valid conclusions. It is also possible to have chains that snake back to where they start. These are called loops. Some people call them nice loops, but I'm not sure what is so nice about them. To me, they are just loops. Ha ha ha. If a chain alternates strong and weak links and loops back to where it starts and has an even number of links and an even number of nodes, then this is a perfect loop and is referred to as a continuous loop because there are no deviations. In this type of loop, you can start with either a strong link or a weak link, and you can choose any node of the chain to call your starting point, and you can proceed in either direction. It doesn't matter because the loop is perfectly continuous. The amazing thing about continuous loops is that once you have correctly constructed one, all the weak links actually become strong links, which can sometimes lead to large numbers of candidate eliminations in one operation. A continuous loop that uses only one digit is sometimes referred to as a fish cycle or an X cycle. An X-wing is actually the simplest form of a continuous loop or X cycle. And because an X-wing is really a fish pattern, this is where the term fish cycle comes from. So let's see what this looks like. Here in this diagram, we have an X-wing on candidate 3 with the base sets in row 2 and in row 6, and the cover sets in column 4 and column 7. And so we know that one of those 2 3s in the green cells in row 2 has to be true, and one of the 2 3s in the green cells in row 6 has to be true. So the only way this can be solved is either like this or like this. So one of those green cells in each of those columns must contain a 3, and that's why we can eliminate all those other candidate 3s from those 2 columns. But there is an entirely different way to look at this. This X-wing is composed of 2 X chains at the same time. If we start on this 3, there's a strong link to here, and then a weak link to here, and a strong link to there. Okay, so let's draw that chain. We have strong, weak, strong. Okay, so we know that one of those 2 endpoints in column 7 must be true, and so we can eliminate all those other 3s in that column that lie outside the 2 endpoint cells. So this is the same result as we get from the X-wing, and we can do it the other way. We can go strong, weak, strong. And by doing it that way, we can eliminate all the 3s in column 4. But if we complete this chain and make a weak link up to that 3, now we have a continuous loop. We have 4 nodes and 4 links, okay? And they go in a circle, and it's just strong, weak, strong, weak, strong, and you can just keep going around and around forever. So as a result of those 2 X chains, the weak links in columns 4 and 7 actually become strong links because there's an effective strong link between the 2 3s in the green cells in column 7, and there's an effective strong link between the 2 3s in column 4 by virtue of the chain. And a continuous loop doesn't have to be in a circle like this. It can snake all around the puzzle, but the idea is that it comes back to where it starts, and that's why they call it a loop. So this is what happens when we have an X chain where the two endpoints lie in the same house. You can eliminate all other instances of that X-digit candidate from the whole house because there is an effective, strong link between those endpoints. So either the two yellow threes are true or the two blue threes are true, even though we don't know which. But that still allows us to make all those candidate eliminations. All right, let's see what this looks like in a real puzzle. All right, here in this puzzle, let's turn on the filter for candidate 8. And we've got an X-wing in these 4 cells, okay? But instead of looking at it as an X-wing, let's look at it as an X-chain. So we go strong, weak, strong. All right? So let's draw the two chains one at a time. First, we have a strong link here, and then we have a weak link here, and a strong link here. So there's an X chain. So that tells you that all those other 8s in row 3 outside the blue cells have to be false because one of those two endpoints must be true. So now let's do it the other way. We've got strong, weak, strong. So this tells us that all the other 8s in row 6 outside of those blue cells must be false because one of those two endpoint 8s must be true. But we can complete this by making a weak link between these last two 8s, and now we have a continuous loop, and those two weak links become strong links, and so you get the same result. All these 8s must be false. Whether you look at this as an X-wing, two X chains, or a continuous loop, you wind up with the same result. Now let's take a look at how this applies to a swordfish. All right, let's turn on the filter for candidate 9, and we've got a swordfish in rows 2, 5, and 8. And luckily, there's a conjugate pair in each of the base sets, and that's going to allow us to make 3 separate X chains. So let's start on this 9 in row 2, column 4, and we have a strong link, a weak link, a strong link, a weak link, and a strong link. Okay? So that means there is an effective strong link between these two 9s in column 4. So we already know from the swordfish that we can eliminate all other instances of candidate 9 from the cover sets, which here are columns 1, column 4, and column 7. So they would be here, 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 and here, and here, and here. So you could eliminate all those red-colored 9s by virtue of the swordfish. But let's draw that chain that I just marked out. We've got strong, weak, strong, weak, and strong. So there are the two endpoints, the blue and the yellow 9 in column 4, which means you could eliminate all 3 of those other candidate 9s in column 4. So now we can make 2 other chains. This time we'll start on this 9 and go here. That's a strong link. And then there's a weak link. And here's a strong link. And then here is a weak link. And then finally a strong link. So now our 2 endpoints are in column 7, which means you could eliminate those 2 red-colored 9s in column 7. And then the last chain would be starting in column 1, and we can make a strong link, and then a weak link, and then a strong link, and then a weak link, and finally a strong link. So there's an X chain with those 2 endpoints in column 1, and which means you could eliminate that 9 in row 4, column 1. But if you connect this chain and make a weak link to this other candidate 9 in column 1, you don't have to make 3 separate X chains. You can eliminate all those red-colored 9s because you know all those weak links are effective, strong links because of the continuous loop. Okay? All right, so now let's take a look at some of these that are not X-wings or swordfish. All right, here in this puzzle, let's turn on the filter for candidate 7, and we have an X chain starting here. There's a strong link, there's a weak link, a strong link, a weak link, and a strong link. So here are the two endpoints, and they lie in the same house, okay? So that means all other candidate 7s in that same house, which is block 2, can be eliminated as false. So all these 7s would be false, those 4 7s, okay? But let's put them back in, and let's draw the chain. We've got strong, weak, strong, weak, and strong, okay? But now, if we connect this last link and make a weak link between those two candidates, now we've got a continuous loop which tells us that all those weak links are strong links. They're effective strong links because you could remove any one of those weak links and you'd be left with an X chain. So that means wherever there's a weak link, you can remove all other same digit candidates from the rest of that house. Now let's get rid of those arrows. So we had a weak link in block 2, so that means these 7s are all false, right? And we had a weak link in row 7, so that means this 7 is false. And we had a weak link in column 1, so that means this 7 is false. So because of that continuous loop, you can eliminate all 6 of those candidate 7s. All right, let's look at another one. Okay, here on candidate 4, we have an X chain that starts here. There's a strong link, a weak link, a strong link, a weak link, and then a strong link. And the endpoints lie in row 7, so they're in the same house. And when you have an X chain where the endpoints lie in the same house, you know you have a continuous loop. So that means we can eliminate all other candidate 4s wherever there's a weak link. So there would be a weak link here in row 7, so that 4 would be false. And there's a weak link in column 8, so that 4 would be false. And then there's a weak link in block 4, so these two 4s would be false. Now I'm going to try to save a little time by just superimposing the chain. So there you have a continuous loop. There are 6 nodes and 6 links. A continuous loop will always have the same number of nodes and the same number of links, and that will always be an even number. So here it's 6. We have 6 links and 6 nodes or 6 candidates. All right, let's do another one. All right, here on candidate 8, we have an X chain of 7 links. So here's a strong link, a weak link, a strong link, a weak link, a strong link, a weak link, and a strong link. But our two endpoints lie in block 3. So that means we have a continuous loop. And so wherever there is a weak link, we can eliminate all other candidate 8s from that house. So there's a weak link in row 7, so those two 8s are false. And then this was a strong link, so the weak link is here in row 5, so that 8 is false. Then that's a strong link. We have a weak link up to this 8, so that 8 is false. And because the two endpoints lie in the same block and one of them must be true, we can eliminate that 8 as well. So all those 8s are false, and again, let me superimpose the chain very quickly. So there's your continuous loop, and this time we have 8 nodes and 8 links. As I said, there will always be an even number of nodes and an even number of links. And when we get to the formal tutorial on continuous loops, you're going to find out that they don't have to all be the same digit. We can use all the candidates, and we can even have links within cells. Of course, when there's a link within a cell, it will be between 2 different candidates, but all those same rules will apply. All the weak links will become effective, strong links. All right, let's do one more, and then we'll wrap it up for today. All right, this time on candidate 2, we have a strong link, and then a weak link, a strong link, a weak link, and then a strong link. And our two endpoints lie in column 9, so we have a continuous loop. So we know that wherever there's a weak link, we can eliminate all other candidate 2s from that house. So there was a weak link in block 5, so that 2 is false. There was a weak link in row 7, so that 2 is false. And there was a weak link in column 9, so that means these two 2s are false. And let me superimpose the chain like before. So there's your continuous loop. This time there were 6 nodes and 6 links. Because the loop is continuous, this means that either all the blue-colored candidates will be true or all the yellow-colored candidates will be true. So any other same digit candidate that can see both a blue one and a yellow one must be false, and this is the case for any other same digit candidate that lies in the same house as one of the weak links. In each of those houses, either the blue one is true or the yellow one is true, so all the other ones in that house must be false. All right, that's going to do it for today. I want to say thank you to all of you who stuck around for this marathon tutorial, and I hope you gained something from it. So let's go back outside and finish up. Okay, so that was pretty easy, right? In the next video, video number 28, we will learn about XY chains. These are simply chains of bi-value cells. We got a taste of this in video number 23 on XY wings. Just like X chains are longer versions of turbofish, XY chains are simply longer versions of XY wings. It will be a piece of cake, I assure you. So I hope you will join me for that lesson as we march toward our goal of your becoming a real Sudoku expert. Until then, be well and be happy.